conjecture is like an easy version of that. All I mean is that, like the Weil conjectures, people have been able to prove them. A lot of geniuses worked on it and were able to prove it. Whereas the Riemann hypothesis, we're still pretty clueless about. So to get interested in the Weil conjectures, one way to think about it is it's like a baby version of this super hard problem of the Riemann hypothesis. And so in this variant version, what you're trying to do is you're not trying to count how many primes are less than or equal to n. You're trying to count how many points an algebraic variety has over a finite field. So what's an algebraic variety? Well, for a first approximation, a pretty good first approximation is that it's just some shape that's described as the solutions of a bunch of polynomial equations and a bunch of variables. So if you know like 5 variables and you write down 3 polynomial equations, that picks out an algebraic. The solution to that is called an algebraic variety. And you can look at solutions that are complex numbers. You can look at solutions that are real numbers. You can look at solutions that are rational numbers. They're all interesting to study, and they're all related in interesting ways. And basically, to make sense of a polynomial equation, you're in good shape for sure if you're working over, if you're looking for solutions in a field. So a field's just a mathematical gadget where you can add, subtract, multiply, and divide. And the Weil conjectures are about algebraic varieties over finite fields. And all you need to know about finite fields for this talk is that there's a bunch of them, and there's one of them for each prime power. So for example, the integers mod 10 that Kevin was talking about last time, that's not a field, because like 5 doesn't have a reciprocal in the integers mod 10. But if he picked like the integers mod 7 as his working example, then we'd be good. The integers mod 7 are a field, and they're the field with a prime number of 7 elements. So for any prime, there's a really easy to describe field with that number of elements. It's just the integers mod that prime. And then there are these more slippery guys, which are finite fields that have a prime power, like 7 squared elements. And you can think of them as sort of analogous to the complex numbers. You get the complex numbers from the real numbers by throwing in a square root of -1. You can get these fields with a prime power of elements, starting from a field with a prime number of elements, and then throwing in some solutions to some polynomial equations that didn't have solutions already in that finite field. But even that I've said is like more than you need to know. So you just really need to know, for the purposes of this talk, is that there's a field whose number of elements is any power of any prime. And so what's nice about that is that because it's finite, if you write down a bunch of polynomial equations and you're trying to count the solutions of them, you can actually count them. They'll be finitely many, because they're just finitely many numbers to begin with. And so the Weil conjectures are giving a formula for the number of points of an algebraic variety, any algebraic variety approximately, any algebraic variety over a finite field. And it turns out that it works sort of like the Riemann hypothesis, namely, there's a main term, a simple formula for approximately how many solutions your equations will have. But then there'll be some correction terms, which will be some wave-like corrections that you have to add to the main term to get the exact answer. And actually, because it's a finite field, you don't have to add infinitely many corrections. You just need to have finitely many corrections. And then here's the real point, which you've seen if you've been looking at my slides, that each one of these correction terms corresponds to a motive. The main term also corresponds to a motive. So I raised this puzzle with the Riemann hypothesis. What do the zeta zeros actually mean? And I didn't really tell you, except that they gave you these wave-like corrections to the prime counting function. But in the Weil conjectures, which people have actually proved, people know a lot more. They know something about what these wave-like corrections are, or what they correspond to. And they correspond to these still somewhat mysterious things called motives. And the idea is roughly that you could take your algebraic variety, your thing of all the solutions of this bunch of polynomial equations, and in some very sneaky abstract way, you can chop it up into pieces called motives. You can't really think of these pieces as geometrical entities exactly. Sometimes you can, but sometimes you can't. So they're sort of cool and mysterious, but there's some abstract sense in which you can chop your variety up into motives, and each one of these motives will contribute a certain amount to the number of points of the variety, and you just add them up and you get the number of points in your variety. And there's a main one, which contributes sort of the bulk of the points. And then there are these other ones that contribute these wave-like examples, wave-like corrections. So you can see what I said example because let's look at an example. So the point is you don't have to be a genius to like try to like discover that this phenomenon is going on. So let's take a polynomial equation and let's try to count its points. So I picked an equation in two variables, y squared plus y equals x cubed plus x. I was just recommended by somebody that like this, hey, this would be a really easy one to do. And I'm going to look at the number of points over the field with 2 elements, and then the field with 4 elements, and then the field with 8 elements, and so on. So remember, there's a field with p to the n elements for any power n of any prime p. So I'm going to take the simplest prime. Well, it's actually the weirdest prime 2. It's sometimes been said that 2 is the oddest prime because it's oddly even. But it's nice and small. So like you could just, while I'm giving this talk, you could like, if you know how to add and multiply mod 2, you could just like figure out what are all the solutions of this in the field with 2 elements. And well, it turns out to be incredibly easy. I'll give it away. Everything is a solution. So y could be either 0, 1, or x could be 0, 1, and as you get a solution here, because 1 plus 1 is 0, and 0 plus 0 is also 0. So everything is a solution in that case. And so for the first row of this chart, you get 4 solutions. So then it's a lot harder to calculate the number of solutions as you go up to 4 and 8 and 16 and so on. But you could probably write a computer program to do it if you're, well, you'd have to be pretty good because you'd have to know how to teach the hardest part would be getting the computer to know how to calculate over these other finite fields. But anyway, one can do it. And so if you look at the number of solutions, you see it's really interesting how it goes, right? So it goes 4, 4, 24, 24, 64, 144, 224, 544, 1024. There are all sorts of interesting patterns in those numbers if you stare at them. Now, people like to talk about how Grothendieck, never deigned to actually look at specific numbers or anything, and that may or may not be true. But certainly, you can get a lot of interesting insights into these type of problems by just grinding away numbers and seeing what patterns you get. So of course, I can't resist mentioning one obvious pattern, like the one that jumps out at me now first, which is a completely useless pattern, is that they all end in the number 4. Okay, I had to say that, but I don't even know why that's true. But more interesting is that it's growing sort of exponentially. It's sort of like the number of elements in your field, right here. Sometimes it is. So sometimes it's exactly the number of elements in your field. Sometimes it's less, sometimes it's more. And so it seems to sort of roughly track the number of elements of your field. So a really good thing to do next would be to take the number of solutions and subtract off the number of elements in your field to see what other stuff is going on, right? Just sort of an exploratory point of view. So let's do that. So that's what this chart shows. And you can see it's a reasonable thing to do because if you think really naively, if you've got one equation with 2 unknowns, if you were dealing with like linear equations, you could say, oh, that's just like having one variable that you get to pick, and then the other one is determined. So it's just like having one unknown, really, one variable. So if that were true, then you'd naively guess that over the field with p to the n elements, there'd be just that many solutions. In other words, like x could be anything, and then it would determine y. Of course, that reasoning is flawed because it's a nonlinear equation. And it's not true that if you know X, you can solve for Y. But if you make that stupid guess, you'd get what I was calling the main term, just 2 to the n solutions over the field with 2 to the n elements. And so here what I'm doing is drawing the true number of solutions, and I'm subtracting out that main term, which was just a power of 2, to see what else is going on. And you see now that like all sorts of cool other stuff is going on, right? You see right away that like these are all powers of 2. You see that they grow more slowly than the main term. The main term is just, by the way, it's just p to the n. So they grow more slowly than that. Can someone else like say some other pattern they see in this list of numbers here? You can be vague. It doesn't, you don't have to give me like a formula or anything. This is just like stuff that you notice.
The error is either 0 or a power of 2 up to sign.
Yeah, it's 0 or a power of 2. It can be positive or negative.
Except for the first one, all the others are multiples of 4.
They're all multiples of 4, in fact. You notice what's going on with the zeros?
0 is every 4.
Yeah, every fourth one is 0. Every fourth one is, so every fourth one is 0. They have an interesting pattern of signs where the first batch of non-zero ones goes negative, positive, negative. The next one goes positive, negative, positive. And they will actually continue doing that. They'll alternate between negative, positive, negative, positive, negative, positive. I should have made the chart much longer, and then you'd like to see the sort of naive patterns that you see from this part. They just keep on going on. So there's a kind of period 4 thing going on, but there's also a period 8 thing going on relating to the fact that this goes negative, positive, negative, and it goes positive, negative, positive. So there are all sorts of patterns that are pretty easy to spot. And so that suggests that this is like a good thing to think about, right? If it was just random junk, then you'd say like, oh, this is too complicated to understand. But this is the kind of thing that led Hasse to think about this type of question. So this particular type of polynomial equation is a kind of equation that describes a certain kind of algebraic variety that people call an elliptic curve. And so Hasse was busy trying to understand the number of points on elliptic curves. And this is an example of that. Well, you can, from the pattern that we sort of began to see, you could like guess a formula for the number of points that made it have that period 8 phenomenon and the minus signs and the alternating and so on. And if you thought about it a while, you'd guess that it's this. It's 2 to the negative n minus some number to the n minus the complex conjugate of that number to the n. So that like when you add those up, you get a real number, you know, an imaginary number in the answer. And these two funny numbers, -1 plus I and -1 minus I, they're complex conjugates of each other. They both have, well, because they're complex conjugates of each other, they both have the same absolute value. But the interesting thing is that the absolute value isn't just anything, it's the square root of 2. 2 was like the number that we were thinking about. We're working over the field with 2 elements and everything seems to be involving powers of 2. But this correction stuff involves these other funny numbers whose size is the square root of 2. So this first term, the main, what I was calling the main term, when you're counting the number of solutions, is just 2 to the n. But then there are these 2 wavy corrections. They're wavy because when you exponentiate a complex number, you get waves. These wavy corrections grow at a slower rate. It's like square root of 2 to the n. The absolute value of correction terms is the square root of 2 to the n. I think I need either a longer arm or, yes, a beam of coherent photons. So, yeah, so that's easier. Yeah. So, yeah. So square root. So these grow out like square root of 2 to the n. So that's sort of a cool pattern. And so Hasse in 1933 he showed that it always works like this for this certain kind of equation that's called an elliptic curve. And I don't think I'll even bother telling you like which kinds of equations give you elliptic curves, because that's not so important. But there's a bunch of polynomial equations in two variables with integer coefficients. A bunch of them, say cubic ones, not all of them, but a bunch of them give you something called an elliptic curve. And when that's the case, then this thing that we've seen happens, namely that the number of solutions in the field with some prime power of elements is just that prime power. Remember, that's your naive guess that you guess if you just assume that you've got two unknowns in one equation. It's just like having one variable that could be anything in this field with p to the n elements. So that's your naive guess. And then there are these wave-like correction terms. And they're just like what we saw. It's like some number to the n minus some number to the n minus its complex conjugate to the n, where that number is some number whose absolute value is the square root of p. So this correction stuff grows more slowly, but also oscillates, well, compared to this exponentially growing thing here. So this is great. This is like amazing that you could like count the number of elements and count the number of solutions, and it would have such a nice formula. Now, it turns out that when you think about algebraic varieties, it's really good to use the ideas of projective geometry. And the idea of projective geometry is that in addition to studying ordinary solutions, you should study solutions where some numbers can become infinite. So you take your usual set of solutions and you put on points at infinity. In this particular case, because there's just like one, well, there are two variables and one unknown. It turns out that you just need to stick on one extra point at infinity, and then you convert your algebraic variety into something that's called a projective algebraic variety. This whole idea of points at infinity, by the way, goes to Renaissance painting, where they realized that, like, if you're looking at a field that it stretches off on and on, there's this horizon, and the horizon is like points that are infinitely far away. And so you've got the plane that you're seeing, and then these points at infinity. And so that's called a projective plane. But it turns out to be a really incredibly potent idea. In this particular case, all it does is it says that if you really think of your elliptic curve in this projective way, you get one extra point. It's a point at infinity. So the answer changes by adding one. And the really cool part is that when you look at elliptic curves over the complex numbers, that is, if you look at complex solutions to this kind of equation that we saw, and you include that point at infinity, then the space of solutions looks like a donut. Well, it looks more precisely like the surface of a donut. It looks like a torus. So one way to think about an elliptic curve is it's a curve that you can describe with polynomial equations, that if you include the point at infinity and you look at complex solutions, it's the surface of it looks like the surface of a torus. That's basically a definition of an elliptic curve. You can define it that way, at least over the complex numbers. That's a good way to define it. Now, an interesting thing about a torus is that you can think of it as having like a two-dimensional part and then two one-dimensional parts, which are these circles, and then a zero-dimensional part. So like you can take a torus and you can unroll it or cut it open and unroll it, and you get a square where the edges are identified. And then you see there's like the middle of the square, everything except the edges. That's the two-dimensional part. And then there are two one-dimensional parts, because remember, this edge is the same as this edge in the torus. And then there's this one. So these two one-dimensional parts, and those, when you fold it back up, those are those two circles there. And then there's this corner, which looks like there are four corners to the square, but they all get identified when you curl it back up. So those four different parts of the torus turn out to correspond to the four terms in this formula here, amazingly. I mean, it's amazing for a bunch of reasons. One is that this is all happening with complex numbers. We're looking at complex solutions, whereas our original problem, we were talking about solutions over a finite field. But this is exactly what led Grothendieck to try to understand how algebraic varieties over finite fields could be understood as having some kind of topology, as if they were over the complex numbers. And so he invented this subject called Étale cohomology to make that precise. And these things that I'm calling pieces you would call, you would describe in terms of cohomology. So some of you know some topology, and so you know that like the cohomology of a torus has a 0-dimensional part, and it has two 1-dimensional parts, and a 2-dimensional part. And so what's cool is that these parts come in different dimensions, and the parts of dimension k in this formula, they give terms whose absolute value at least grows like p to the k over 2 times n. So this grows like p to the n, that's coming from the 2-dimensional part. These guys grow like square root of p to the n, or p to the 1/2 n. And that's because they're coming from the 1-dimensional parts. And then this grows like p to the 0 times n. It's just 1. Doesn't grow at all. And that comes from this point here. So that's the idea of motives, that we're able to take the elliptic curve, take the solutions of our original equation, which was on previous slide, and in some sense break it up into 4 parts that each contributes some amount to the number of points, the number of solutions of your equation. But although it looks very vivid here, how I'm chopping the torus up into these 4 parts, you have to realize in some sense that's an illusion, because these numbers here, these can be negative. They can be positive or negative. So these 1-dimensional pieces here can, for some mysterious reason, contribute a negative number of solutions to your equation. So that's why motives are mysterious and interesting. We have to work to try to figure out what the heck is going on there. So historically, my very quasi-historical account here, don't hold me to historical accuracy, but Baez was famous in part because while he was a prisoner of war, he generalized Haas's result to curves of arbitrary genus. So over the complex numbers, in addition to elliptic curves, you have other kind of curves that can look like the surface of an n-hole donut, or I guess you say a g-hole donut. The number of holes is called the genus G. And so he generalized Haas's result in the sort of, anyone would have guessed this generalization. Proving it is the hard part. If you have a smooth algebraic curve of genus G, now defined over the field of p elements, the number of points. Oh, I should say that like once you have an equation that's written down that makes sense in the field with p elements, that same equation makes sense in the field with p to the n elements for larger n. So then you can talk about how many points there are over that larger field. So this, you may be, if you haven't thought about this stuff, you may wonder like, how did it switch from being p to the n? Well, the point is that just like you could write down an equation with a polynomial equation with real numbers, but then you can look at complex solutions. It's a bigger field. That's what's going on here. So anyway, the number of points follows the exact same pattern. You get p to the n minus a bunch of these corrections, 2g of them, and then plus 1. And all these corrections grow like powers of different numbers, but all those numbers have the same absolute value. They're all the square root of p. I should say that if I like took this genus 2 surface and I chopped it up into, if I drew little lines on it, like I did here to sort of chop it up, there would be 2g of those lines or circles. And so that's why we get these two, that's roughly why we get these 2g parts here. So it took him a long time to prove this. He sort of announced a rough proof in 1940, and it required lots of filling in, but he had lots of spare time because he was a prisoner of war. And luckily, they like let him lead a seminar on algebraic geometry in the prison. So let's look at this really simple example. The projective line, which in the complex numbers, you would call it the Riemann sphere. So it's the complex numbers plus 1 extra point at infinity. The projective line is just like the ordinary line, but with 1 extra point at infinity. So if your field has p to the n elements, and we often call that number q, then it will have q plus 1 points. And in this case, it's easy to see what's going on. You can split the projective line into the ordinary line, which is the number line, which in this case is fq, which has q points, and 1 extra point at infinity. And you're familiar with that example over the complex numbers. So in that case, this Hasse formula or this Baez formula is incredibly easy to prove. As basically did, and the decomposition of the variety into these mysterious pieces called motives is not mysterious. It's just the decomposition of the sphere into a plane and 1 extra point. Well, a plane, but it's called the complex. It's a copy of the complex number, so we should call it a line because it's a one-dimensional vector space over the complex number. And by the way, that works in higher dimensions too. So besides the projective line, there's a thing called the projective plane, and the projective plane is the ordinary plane plus a projective line at infinity. And the projective line is an ordinary line plus a point at infinity. So it's sort of recursive in that way. And so the projective plane breaks up into a copy of your field squared. It'll have, this is the field with q elements. So it'll have q squared elements. And then there'll be this projective line at infinity, which is an ordinary line, which has q elements. And then this point that it has at infinity, which is 1 extra element. And so the total number of elements is q squared plus q plus 1. So now what we're doing is we're looking at things that are like, they're projective varieties, but they're not curves anymore. They're not just a one-dimensional thing. So that's why we're getting a q squared here. And we're seeing that there's still a similar kind of pattern going on that we saw in the, right. So this is a one-dimensional thing. Don't be fooled. That's one complex dimension. But this is like a two-dimensional thing. And we're seeing that there's still a similar kind of formula that works. And in fact, that works in any dimension. So if you're working with the complex numbers, you can look at this thing called projective space of dimension D. And now I'm bringing in the word coilology for the first time for serious. But what I'm mainly using it for is to say that you can actually chop that thing up into pieces, which are like the main piece, which is just a copy of c to the d, and then a thing at infinity, which is like c to the d minus 1. But then it has a thing at infinity, blah, 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 recursively. So you can chop it up into these pieces. They're actually called Schubert varieties. I forgot to change the slide here. And so that same argument works. I mean, it wasn't an argument, but the same argument that you could use to establish that, you could use over any field. And so with the field with q elements, this projective space breaks up into these different pieces. And so the number of points follows the same kind of pattern that we've been seeing before. So I'm saying that for higher dimensional things, you can often count the number of points and you get this main term plus lower order terms. And there are even other cases where that works. There are these things called flag varieties that you can chop them up into these pieces and just count the number of points in each piece and add them up. And it's pretty easy. But the thing is that most varieties don't work out so easily. And I already illustrated like how things get weirder, like elliptic curves illustrate the subtleties, because elliptic curves have both, if you think of them as over the complex numbers and think of it as a torus, it has both even and odd dimensional stuff in it. It has this two-dimensional body and then some one-dimensional parts and some zero-dimensional parts. Whereas these other kind that I was talking about, they don't have that mix of even and odd dimensional parts. So that's one thing that's weird about elliptic curves, but that's actually typical of varieties that they have that weirdness. It's just these special kinds that don't have that weirdness. And the other thing that's even weirder is that, well, it's connected, is that when you count the number of points, it's not just a polynomial in Q. As we've seen, it's Q P to the n. Plus then these other things that have that involves the square root of P to the n. This is like square root of this thing here grows like square root of Q. And these other things can have negative signs in them, which means that you're not counting points in some actual thing anymore. So Baez conjectures, which have different parts, have this sort of crowning part called the Riemann hypothesis over finite fields. And this is a generalization of the Hasse result and the Baez result to smooth projective varieties of any dimension. So if you have one of dimension d over the field with p elements, you can count the number. It's a formula for the number of points defined over the field with p to the n elements. And this looks sort of scary at first, but basically you add up from k going to 2d. So those are dimensions of pieces. The dimensions of the pieces go from 0 on up to 2d, because like an elliptic curve is a one-dimensional complex variety, but when you actually draw it, it looks like a two-dimensional donut. So the real dimension is double the complex dimension. So you get these pieces going from 0 to 2d, and then there could be a bunch of pieces of dimension k. Beta k, it's called the kth Betti number of the variety over the complex numbers, and it's basically the number of k-dimensional pieces that you need to make that variety. So that's telling you how many terms you get, and then each term is going to be basically some number to the nth power, where that number, its size is p to the k over 2. So this is maybe a little confusing, but it's just a generalization of what we saw for the curves, where we had like, for curves, we just had this p to the n part, and then it's like p to the square root of p to the n type stuff, and then it's p to the 0 type stuff. So that just like keeps on going if you get higher dimensional things. And also you'll notice there's this alternating minus sign thing, depending on whether k is even or odd. And we've already seen that showing up here, that like the first term, the two-dimensional, coming from the two-dimensional part of the torus, that's his plus sign, and the stuff with the one-dimensional parts comes with a minus sign, the stuff with the zero-dimensional stuff comes with a plus sign again. So that just keeps alternating like that. So this is the Riemann hypothesis for varieties over finite field. So basically the summary for policymakers is that the number of points of one of these varieties, it has a main term plus a bunch of wave-like corrections that you add to it. And it's understanding those wave-like corrections. It's the fun part of the Riemann hypothesis. Now, usually people phrase this conjecture in terms of some function called a zeta function. It's not the original Riemann zeta function, it's some kind of mutant zeta function that works for this particular variety. And when you phrase the conjecture that way, which is completely equivalent to what I said, then it says that this zeta function has zeros on poles on certain lines where the real part of C is 0, 1/2, 1, so on. So that makes it look more like the old Riemann hypothesis, but I find that whole way of thinking about it is like too confusing when you're just getting started, because basically what the zeta function is doing is it's like a trick for taking the count of points and rewriting it in terms of some function. And it just becomes less intuitive what's really going on, which tried to make it intuitive that what's going on is that we have a formula for the number of points, the number of solutions of a bunch of polynomial equations. And all these facts about that formula are the Riemann hypothesis. So here's the formula again. And so Grothendieck's dream for trying to prove this, at some stage in his trying to prove this, his dream became that you can actually break the variety into these very abstract chunks that aren't subsets called motives. And they have dimension 0, 1, blah, 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 on up to 2D. And there can be a bunch of them of dimension k. And this inner sum here is summing over all the different motives of dimension k. And the k-dimensional motives contribute the terms that you see here that look like this. So each chunk just contributes a certain term to this sum, but the weird part is that it could be a negative number. So there's no way that these motives can always be subsets of your variety. There's some mysterious things, and that's the whole mystery of motives. What are these things? What are these things? What type of thing could they be? Okay, now I'm going to launch into some category flavored stuff. So far what I've been doing, which is like the important part of the talk, is just try to get you to wonder what motives are and have some idea of like why you should care. You should care because if you're trying to count the number of solutions of a polynomial equation over a finite field, the answer is always going to be a sum of terms, and those terms are called motives. They come from these things called motives. Okay, but what are motives? Well, here Grothendieck had a guess as to what motives were. And so there's a category of smooth projective varieties. And there's a kind of map between smooth projective varieties. It's the right kind of map that I believe is called a regular map. So there's a category of them. But what we're going to do, what he's going to do is he's going to take that category and map it to some other category called the category of motives. People usually use the opposite here. It's just a pure convention. It's sort of distracting right now. I've been a better pedagogue. I would have hidden that, but I just couldn't lie that much. But it doesn't matter at all. It's just a convention. So now there are lots of different things called motives because people have been flailing around trying to get something to actually work. But I'm going to talk about one kind, which is, I think, Grothendieck's original kind called pure child motives. So I'm just going to call them motives. And the main thing about this category of motives is that it's a lot like the category of vector spaces. It's a lot like categories that you're familiar with from linear algebra. In particular, if you've got two motives, the set of morphisms from one to another is a vector space. So that means like you can add maps between motives. And composition is linear in each when you compose linear in each thing. So that's like completely different than the category of varieties. You can't add maps between varieties because there's like spaces. You can't add maps between spaces usually, but you can add maps between vector spaces. So it's a linear category, and it's very nice as such. It has direct sums. So there's a concept of direct sum, or if you really want to show off, byproduct between in these kind of linear type categories. And it also has the property that if you have a map from a thing to itself, then when you do it twice, is you get the same thing. It's called an idempotent. Then it's actually going to be projection onto a direct summand in X. So like if you've got a big vector space, it's the direct sum of two, you can project the whole vector space onto one of them. And that map will be idempotent. And this is saying that any idempotent arises that way, which that's true in the category of vector spaces. And then also you can take tensor products of motives, which is coming from the fact that you can take products, plain old Cartesian products of varieties. So there's a thing called tensor products of vector spaces, and it makes vector spaces into a symmetric monoidal category. So we want motives to have this property too. So all three of these properties are properties that are true of the category of vector spaces. And so the idea is that we're dreaming up this category that lets us take our problems with varieties and move them over into this category that's more like the world of linear algebra. And that's the world of motives. And we're going to try to take our variety and turn it into a motive, and then break it up into a direct sum of these basic building blocks, which are going to be the motives. So for example, you can see some stuff that you can do with that. You can map the whole projective line, not even sphere, but P1, we call it the projective line. You can map all of it to a single point. So that gives you a map from the projective line to itself. It maps it all down to whatever your favorite point is. And clearly, if you do that twice, it's the same as doing it once. So by those axioms, by that Karoubi completeness business, that means that the motive for P1 is going to be, or you can map it to itself in a way that's idempotent. And that means that it can break up as a direct sum of two pieces. One of those pieces, it'll turn out, will just be the motive for the point. But the other is the rest. And that's called the Lefschetz motive. And that's an incredibly important motive. Basically, you can think of the Lefschetz motive as sort of like the rest of this stuff that's not the point at infinity. So you can think of it as line, the projective line, the non-projective line, the ordinary line. That's another reason why it should be called L, but it's named after Lefschetz, which is why it's called L. So I said before that we could take this simple example, we could actually like chop it up into two parts, right? We could chop it up into the point of infinity and then a copy of our field. Well, here we're doing that. We're doing that in the world of motives. And similarly, you can do that for projective spaces of any dimension. So like if you have an n-dimensional projective space, you can chop it up into pieces. And there'll be like the thing that comes from a point, and then the thing that comes from the Lefschetz motive, and the Lefschetz motive tensor itself, all these powers. And then that's a way of understanding the formula that we saw for how many points there are in projective n space, which is 1 plus q plus da, da, da. So the idea is that we should think of this Lefschetz motive as a thing that has q points, and then its square has q squared points, and so on. Now, the Lefschetz motive is like the easiest motive to understand because you can actually visualize it. It's basically just the line. It's just a copy of your field. That's the visualizable case. And it has, non-negative number of points. So you can actually see it as a subset of your sitting inside your variety sometimes. But most situations are weirder than that. Like we've already seen that elliptic curves are going to break up into pieces that are weird. They could have like a negative number of points. And so most curves and other varieties, to break them up, we're going to need to use motives that aren't just these tensor powers of the Lefschetz motive. So how do you actually get this category of motives with all these desirable properties? Well, you can actually do it by doing like 3 steps, starting from the category of varieties and doing 3 things, basically to force yourself to get a category that has the properties that I listed. So I said, you want a category where you can add morphisms and where there are direct sums and so on. And so you can basically, if you're a category theorist, you know how to like do stuff to categories. You say like, hey, new category, you can't add morphisms. Okay, I'm going to make a category where you can add morphisms, but the new morphisms will just be sums of the morphisms in the old category. You sort of freely make what you want to be true. And so that's one way to do it. That's one way that you can, if you look at Wikipedia and you look at the definition of pure child motives, they'll list you the 3 steps of how you get it. I don't want to tell you that because it's a little bit boring at first when you first see it. But you can also characterize it using a universal property. There are a bunch of functors from the category of varieties to vector spaces that are nice. They're called vague cohomology theories. And part of what Grothendieck wanted to do is he wanted to make sure that every such cohomology theory you can get by first turning your variety into a motive and then turning your motive into a vector space. And so that's a universal, the fact that you can do that in a unique way is a universal property of the category of motives. And you can just say, I want the category that has that universal property. And that's basically equivalent to this other way of talking about it. And vague cohomology theories have been introduced by Grothendieck and other people to help prove the vague conjectures. And that's how they got their way to motives. They said, oh God, we got all these cohomology theories we're using to try to prove the vague conjectures. Wouldn't it be nice if all of those cohomology theories factored through some mysterious category called the category of motives? So Grothendieck showed that the Riemann hypothesis for finite fields would follow from some conjectures, which he called, with his usual modesty, the standard conjectures. And these conjectures would imply a bunch of stuff, which I'll just whiz through. So one is that if you take any variety, you turn it into a motive, then you can bust it up into pieces which have different dimensions, but they call it weight, actually. So weights going from it's actually like weights going up from 0 up to 2 times the dimension of K, corresponding to that outer sum and that sum that I described. He wanted the category of motives to be abelian. That's like a gold-plated category, like the category of vector spaces, where you can do all the stuff you want to do with linear algebra. He conjectured also that these conjectures also imply that it's semi-simple, meaning that you can bust every motive up into a finite direct sum of building blocks that are sort of like what they're called simple. They have only 0 and the motive itself is sub-objects. So it's like you can really bust things down into these pieces that have no smaller pieces sitting inside them. These are all still unproved. Nobody has proved any of these conjectures. Conjectures are often stated in a different way, but those conjectures imply this stuff here. So this is why the theory of motives is regarded as like difficult or stuck. That you can define this category of motives, but then when you want some of the basic things to be true about it that you like to be true, and we just like nobody knows how to prove it, and actually a bunch of people think maybe they're not even true. No one has disproved them, so they're sort of stuck. And they've done stuff. They've done a lot of good stuff, but this is the sort of the mystery of motives, is the things you would want to get going with a really good theory of motives. Nobody has been able to do. So he wasn't able to prove the standard conjectures. They still haven't been proved. Deligne proved the Riemann hypothesis varieties in 1974 in a way that sidestepped these questions. They're still mysterious. I'll just mention, I started out by talking about the Riemann hypothesis. What about that? Well, people have been trying to get around to that. So in 1995, Yuri Manin wrote a paper, a lecture on zeta functions and motives, where he was trying to generalize the whole idea of motives so that he could prove the actual Riemann hypothesis. And Alan Kohn has been spending a lot of time trying to prove the Riemann hypothesis using these ideas. He's been doing it at least since 1995, probably earlier, of course, because in 1995 he came out with a free book, a book that you can get. It's free. Sorry, that sounds stupid, but he came out with a book. By the way, if you get my slides and you click on this, you'll get a free copy of it from his website, not from Russian again. And it's called Non-Commutative Geometry, Quantum Field Theory, and Motives. There are a lot of connections discussed these days between motives and physics. And I should say that like pure motives that I've been talking about, they're just a special case of something called mixed motives that handle more general varieties that aren't smooth or projective. Those have been even more mysterious. Nobody could even get the category of them, figure out what it should be. But Voevodsky got a Fields Medal because he was able to skip that step and define something that would be the next step, called getting the derived category of mixed motives. And he used it to solve a big open conjecture called the Milner conjecture. So a lot of people are very happy to work with his approach. So in short, motives are getting a lot of the world's top mathematicians interested in them and continuing to work on them. And so someday, hopefully, we'll get the full story about what they are. But you can already begin to learn some stuff about what they are. Thanks.